Hi guys, I'm gonna be honest, I do not feel like recording right now. It's almost 3 a.m. my time, and I'm really tired, but I told myself I would record a video today, so we're doing it anyway. Today we're doing remove stones to minimize the total. So we're given a zero indexed integer array called piles, where piles.I represents the number of stones in the ith pile, and an integer k. And we should apply the following operation exactly k times. So they want us to choose any piles at I and remove floor of piles at I divided by 2 stones from it. So floor just means to like round down, and then whatever index we choose, we just divide by 2 and then round down because we're doing like integer division basically. So they say, notice that you can apply the operation on the same pile more than once. And they want us to return the minimum possible total number of stones remaining after applying the k operations. They say, okay, so yeah, floor at x is the largest integer that is smaller than or equal to x, so it just rounds it down. So if we take a look at example 1, we are given this input array and k equals 2, and we would output 12 because, so the possible scenarios, or steps of a possible scenario are, so we would apply the operation on pile 2, so if we go to index 0, 1, so actually let me just copy and paste this so I can include the indices as well. So 0, 1, 2, oops. There we go. So basically, if we look at pile 2, which is going to be at index 2, this is 9. 9 divided by 2, if we round, so for our integer division would give us 5. But because we are rounding down, it would be 4, because it would be 4, technically it'd be 4.5. And then if we round down, then that's 4, but that's how much we're removing from here. So actually we are leaving 5. So this would turn into 5, because 9 minus 4 is 5. Does that make sense? I hope I'm explaining this well enough. But then this is what our new array would be after that first operation. Then on the second operation, we choose index 0. So 5 divided by 2 gives us 2 in integer division, so we're removing 2 from 5, which would give us 3. Then the total number of stones in 3, 4, 5 is 12, because we've done 2 operations now, because k was 2. So if we add up these numbers now, this is 3 plus 4 is 7, plus 5 is 12, so we would return 12. Okay, in example 2, we're given this input array and k equals 3 this time. So k equals 3, let's just keep a note of that. So this time they say apply the operation on pile 2, so index 2 is 6, so 6 divided by 2 is 3. Then they apply the operation on pile 3, so 7 divided by 2 is 3 using integer division, so we would remove 3, giving us 4. Okay, then we do pile 0, so 4 divided by 2 is 2, no need to round down. And then the total number, because now we've done it 3 times, is going to be 2 plus 5, or 2 plus 3, sorry, which is 5, and then 5 plus 3 is 8, and 8 plus 4 is 12, so we would return 12, as we can see here. So it seems like they want the minimum possible total number of stones remaining after applying the k operations, which means they want, so if there's the minimum possible number of stones remaining, that means we want to remove as many stones as we possibly can. And if we're removing as many as we possibly can, but we're removing whatever index we choose divided by 2, so like let's say, right, if we do this one divided by 2, then we would remove that many stones. Then we want to be picking the biggest numbers that we possibly can, because that means in one like we're maximizing the number of stones we can remove in one operation if we choose the biggest number we can, if that makes sense. So in order to do that, we are going to need to constantly keep track of the maximum in our pile, which will require us to use a max heap. So we're going to use a max heap to do this. All right, so let's initialize that. So priority queue of integers, we'll call it heap, is new priority queue. And we're going to do comparator.reverse order to make it a max heap, because we want to keep track of the maximums. And let's also have a example pasted here so we can refer to it as we do this problem. And I'm also going to just add this array but in sorted order from greatest to least, so that, like, oops, what am I doing? Like, I know, again, disclaimer, this is not actually how heaps are represented, but like for simplicity's sake, I'm just doing this so that we can like look at whatever our current maximum is. So just keep that in mind. Okay. So now we just need to loop through this input array and add all of these numbers into our heap so that it will be sorted. Not sorted, but like, you know what I mean. Workable, like able to get the max. Y'all know what I mean. Okay, so for each pile in piles, we will just add it to the heap. Okay, that's simple enough. So now we basically have our max always at the front now. And then once we have our heap, we are going to need to loop through the heap and do what they're asking us to do here basically, which is for k iterations, we need to remove the maximum and add back the maximum divided by 2 basically. So while k is greater than 0, we'll say the top is heap.remove, because that's always going to be the maximum number. So the first iteration, it's going to be 9, right? Because that's the maximum currently, for example 1 at least. And then we are going to add back that max divided by 2. So heap.add. And I'm going to do this kind of a weird way because we want to, because remember, we want to do this divided by 2, which is integer division, but we want to round down, which integer division already does that, but then we want to remove this amount, but we're adding back the difference of it. So it's actually going to be, like, if we're just doing the division, it's just going to be top divided by 2 like this, but this is how much we want to remove, not how much we want to add back. So to add back, then we want to do the original amount minus this, because that's going to give us the difference. Because if we think about this, right, so top divided by 2, well, top is 9, so 9 divided by 2 is 4. Did I do that right? Yeah. Yeah, okay, so sorry, I had to think about that for a sec. Glitch. So we have, yeah, so this is 4, but we are removing 4. So the number we want to replace this 9 with is actually 5, which is the difference between these two. So that's why we're going to do it like this. Okay, then lastly, we're just going to decrement k in each iteration so that it can actually reach 0 and then we can actually exit the loop. Okay, so this is going to do what we did down here, like these steps and such. But now we just need to return how many stones we have remaining after doing these steps. So like, let's say we got all the way down to here. We have 3, 4, 5, right? So how do we actually calculate how many stones we have? Well, we need to first set up a variable, and we can just call it stones at 0. And then we're gonna loop through our heap and add all of these values to stones. And then we'll return stones. So while our heap is not empty, we are just going to add the values to stones. So then we're going to return stones. And that's it. Let's test that out. All right, okay. So now our time complexity. So, okay. We first, in this loop, we are looping through our piles array and adding each element into our heap. And so adding an element into a heap is going to be log n. So for n elements, that's going to be n log n. Okay. And then secondly, in our while loop, we are, for k iterations, okay, removing something off of the heap, the max value every time, and adding back a value into the heap every time. And then k minus minus is constant, so it doesn't matter. But so remove and insertion are both log n for a heap, but, well, technically, okay, 2 log n or whatever, which is just log n, but we're doing this k times. So that's going to be k log n, which is kind of weird, but k log n, like that. Okay, now our last step is we are looping through the heap and counting how many stones we have, which is just adding up all of the elements. So that is just going to be, however many elements we have in the heap, which is going to be n because it's proportional to the input array. So that is just going to be O of n. Yeah, okay. And then basically if we add all of these up, so O of n log n plus O of k log n plus O of n. Well, this O of n doesn't really matter because we have this n log n, which is bigger, right? So this O of n can exit. And then between these two, we can combine them by saying like n plus k log n, and then delete this. So this is like super weird, but yeah, that's just the case for this problem, I guess. And let's define our variables. So n is the number of elements in piles, and k is just k. I guess we could define it, k is number of operations, because that's what they tell us here, right? K operations. Okay, now let's take a look at our space complexity. So our space complexity, okay, in all of these heap problems, we only, at least so far, we only have this one heap, nothing else, and here we are adding n elements, because we're adding everything that's in piles into it, which is n elements. So that's O of n space, and then we are removing, but every time we remove, we add something back, so this cancels itself out. And here we're not adding anything or removing anything. So our space complexity is just O of n, where n is the number of elements in piles. And that is it for this problem. Thank you guys for watching, and like and subscribe if you found it helpful. Bye!